Okay, so as I said, you can continue working on the quiz, but if you're finished, we open today to page 78 of the packet. And while we're opening to 78, a quick look at the calendar. So today is our second to last class. It's our last day where we cover new material. To be clear, none of the new material we're doing today is going to be on the final exam. All right, this is just kind of a preview of coming attractions for Calc 2, but I'm not testing you on it this semester. On Monday will be our full period review for the test. The test itself is on Thursday next week. Any questions on the calendar? Tiffany? I hope so. Let's see. So could somebody help us out and find the study guide for the final exam? Where is that? Well, maybe it's just here. On the very last page of the packet, it says 3 sheets of reference materials. So maybe the 3 sheets you've already made for the first 3 tests. There was a derivatives handout with all the derivative rules on it, and then the related rates guideline, the worked out example. Good. Any other questions before we dive in today? Okay, and again, the project is still up in the air. You can turn it in to me Thursday of next week. You could also turn it in to me today or Monday if you get it done early. So that's the last thing you'll have to do before the final exam. And so we start here on page 78. And can we go to Ernie for number 1?
This section will see a few differences about definite.
Thank you. Richard, number 2. Okay, so here in number 3, we've got this integral from some number a up to the same number a. Now remember, an integral represents what for us geometrically? Is an area, right? That symbol right there was just our fancy way to write area under the curve above the x-axis between 2 vertical lines. What happens if the vertical lines are at exactly the same spot? It's just one single line instead of having a 2-dimensional area in there. So how much area would you say we have? 0. So if they're both the same number, seems like 0 is the only thing we have, the only choice we have for what that integral should be. And then there's this funny business about, well, what if the numbers are reversed? Instead of going from A to B, what if we go from B to A? So what we do in that case is we say it's still the area, but we define one of them to be the negative of the other one. So if, for example, this thing right here were equal to 7, the area of that part were 7, and you were to, instead of going from A to B, the normal way, left to right, you were to go from B to A, we define that area to be negative 7, okay? So if the numbers are reversed, then you have to negate whatever answer you might have expected in the beginning. And I think there's a good justification for that. Suppose that we're measuring a distance, and I start here at time 0, and then I walk this way, and 2 seconds later I've walked 5 feet. Well, if you were to have a video of this exciting demonstration I've just done here, and you were to watch it backwards, instead of from 0 seconds to 2 seconds, you watched it from 2 seconds to 0 seconds, you'd say, oh, he went negative 5 feet. He went backwards 5 feet. So I think it makes sense to say if you're watching the video backwards, just call it a negative of what you had. So let's do a couple of little examples here. 4a is the integral from 3 to 3 of, and it makes no difference what's in there. What is this integral equal to? That's equal to 0. As soon as you see 2 numbers that are exactly the same on that integral, you raise your fists in glory. It's the easiest integral you'll ever find. Now this one right here, integral from 1 to 0. So already what's weird about that? Yeah, it's backwards, right? The lower number is on the top instead of being on the bottom. So I can't really handle that. I need to write it in the normal way. Small number on the bottom, big number on the top. So I'm going to write it that way because I have a good sense of what this symbol means. But right now I'm saying they're equal and they aren't. What do I put in? A negative sign. So whatever I get from my blue integral there, my normal area, I'm just going to call it negative of that answer. Okay, so, but what do I get? I mean, you could type it into a calculator, but this one we should be able to do by hand. Square root of 1 minus x squared, I've shown you the part of the graph of that function. That function is actually the top half of the circle. And if I'm just going 0 to 1, then I'm only sweeping out that quarter of the circle. What's the area of the entire circle? It's pi r squared. So the area of the whole circle is pi. So the area of that part is just quarter pi. So then this guy equals 1/4 of pi, except that's not the right answer. What's the right answer? Negative that. Okay. So all this stuff that we've been saying about area assumes that the smaller number is on the bottom. If it's not, put a negative in front of whatever you get. Calculator agrees. Okay, so it turns out there's some real nice properties of integrals. Some of them look quite similar to nice properties of derivatives. So first one says, what if you have to integrate the sum of two functions? I'm just going to draw a quick little example here, and then we'll fill in the rest of these things. You know what? Let's do an example for part C. Let's draw that one instead. Okay, so suppose that I've got my function, and I'll just try to draw something not too complicated. Let's say that this is my function here. So that's f of x. And we're going from some number a out here to some number b. And so the integral is just that area inside of that little space. But then I'm saying, all right, I don't want the function just f of x. I want c times f of x, some constant times f of x. If c was the number 2, what does multiplying in front of a function by 2 do to the function? Makes it twice as tall, right? It's a vertical stretch. So I'm going to draw 2 times this function. So if it's a 0, then 2 times 0 is still 0. But this point over here on the right gets twice as tall as it was before. I'll pick this point right here. It gets twice as tall as it was before. And every point gets twice as tall. And then I'll drop that straight down. How do you think the area in this space bounded by the black curve compares to the area, the whole area, bounded by the red curve? Yeah, it's going to be twice as much area. We buy that? Like every y value got doubled. So all the rectangles, if we were drawing rectangles, would get twice as tall. So the area would become exactly twice as much. So what that means is if you have a constant inside of an integral, then you can take that constant in the front, do your regular old integral without the constant in there, and then just multiply by the constant at the end. Double the original area in that case. Buy this? Great. So it turns out there's a similar property that's just as nice for integrating the sum of two functions. Turns out you can integrate the two functions separately. And what do you think you can do with the two numbers that you get? You can just add them together. Right, and it is easy. And it looks just like the rules for derivatives, right? We had some nice derivative rules. If you had a constant multiple and you were trying to find a derivative, would that constant multiple stay or go? It would stay. All right, constant multiple for an integral. It stays. It says do the ordinary integral and then hit the constant at the end. Were the sums nice or difficult for derivatives? If you have 3x squared plus 5x and you want the derivative, easy, right? Just do them separately, plus sign at the end. Same thing is true with integrals. Just do the integrals separately, plus sign at the end. I'm being lazy. They should all have a to b on them. I'm just not going to write it. Same thing here. What do you think happens in part B? Same, but just put a minus sign. I'll get super lazy and just put a minus sign and say, okay, that's that one. And then part D, it's a little bit weird. So first of all, there's only one function in part D. It's just the same f function in both. And the first integral says, go ahead and go from A to C, find some area, and then you go from C to B and you find some other area, and you add those two areas up. So can we figure out what, first can we figure out why I can't move this thing? So take a look at this picture in number 6. So So the first integral up there says go from A to C. So that's this area right here, right? And then the second integral says go from C to B. So that's this area in here. Okay, it was kind of silly. Couldn't we just have done it in one shot? From where to where? From A to B. So we can put that up here. This is really just a single integral from A to B.
Why does it go ACB or ACB?
Because I wanted my final answer to be A to B. That's all.
It doesn't make sense that there's some, like, going back into, like, the, whatever theorem it was, at some point C.
Mean value theorem. Yeah, so we have seen A to B a lot and magical C coming up somewhere in between. Good connection. Okay, let's see if we could do number 7. Again, the goal is to do it by hand. I know the calculator will get it to us. We could just type it in right now. But let's see if we can use some of these nice new properties, get a little bit comfortable with them. So this integral equals. The first thing you see is what in this complication? It's a subtraction, right? There's a 5, there's a 3 radical 1 minus x squared. Subtract, that's nice. Write 2 separate integrals. The integral of 5 dx, subtract the integral of 3 times that radical. Make sure you write the dx every time. Every time you have one of those integral symbols, that elongated s, it needs to have a partner. It needs to have a dx. Okay, let's keep going here. The integral, there we go. The integral of 5, all right, I haven't seen that integral before. Let me draw a picture. I'm trying to graph 5, y equals 5, I guess. What's the graph of y equals 5? Horizontal line. So we're up there at 5. And we're integrating from where to where? 0 to 1. So there's 0, there's 1. What is the integral of 5 dx from 0 to 1? It's 5. It's the area of that rectangle. So there are a few geometrical shapes that we can actually find areas of, and if you happen to get one, then you should be able to just draw a little picture and say, oh, that's just a rectangle. Or something else, maybe it's just a triangle. Okay, then there's the minus sign. Now, if it were just the radical 1 minus x squared, well, we saw that. We did that one up above. How can I handle the fact there's a 3 in the front? We pull the 3 out. It's a constant multiple. So the 3 comes out. You don't need to write it, but I'll put it times just to really highlight we're doing a multiplication. And then you put the integral. Five minus 3 times this integral we saw. What's the answer? It's pi over 4. So there's our answer. 5 minus 3 pi over 4. Any questions on that? So the point of that is just to kind of start us getting some practice with the nice properties of integrals. There are some nice derivative properties. There are analogous nice integral properties. There are some really hard derivative properties. Next semester, we'll see some really hard integral properties. Okay, let's take a look at the next page. And I apologize that the graph at the far right kind of got cluttered up on the right-hand column here. But hopefully we can read what we need to read. So here's the idea. In this diagram, the areas of the regions labeled Roman numerals 1, 2, and 3 are 4, 10, and 7 respectively. So up here is a 4, down here is a 10, and that space in there is a 7, okay? All right, so I'm gonna circle just a few of these and ask you guys to fill in the answers. So can you find part B, part C, part H, and I think that's good. Yeah, with your neighbors, see if you can do those three. How much is the integral from A to B, the very first question? A to B is -10 because stuff below is negative, so that's -10. How about part E, integral from A to C? That's -3, that's the -10 plus a +7, so that's a -3. And then last part H, it says from B to A, that looks an awful lot like the first one we did, from A to B. So what's the answer here? Is +10. So if you're going the wrong way, and the wrong way means backwards, like we're walking almost all the time to the right on the x-axis. If you are walking backwards, you need to put a negative sign in front of your answer. Okay, let's take a look at number 10. It's an old AP question. Ignore the picture that we just looked at. 10 is a completely brand new problem. So it says you have some function, and you know the integral from 1 to 10 is equal to 4, right? And the integral from 10 to 3 is equal to 7, okay? And you want to find the integral from 1 to 3. And so I'm going to ask you guys again to work with your groups, and I will just give you one little highlight here. The only numbers that appear in any of these integrals are 1, 3, and 10, and it is not a coincidence that the numbers I didn't circle are the same as the numbers I did, okay? So you're going to have to use the fact that 1, 3, and 10 somehow are really important in all of these integrals. So with your neighbors, see if you can make any headway on this one. Okay, so we had a few different answers here. We had one group say -3, we had one person say 3, and a bunch of groups said +11. So let's see if we can get some consensus on this one. I need some more space somewhere. I don't really know where I can go, maybe down here. So so for me, I've got a picture. I'm going from 1 to 10, and the entire thing, the whole thing is 4. And then for the other one, 3. So 3 is an important number too. So from 10 to 3 is 7, but that's backwards. I can't handle when it's backwards. So what I could say is that from 3 to 10 is really equal to -7. Okay, so maybe that's useful. So let's compare the integrals that we're looking at now. We've got from 1 to 3, from 3 to 10, and then from 1 to 10. And if you say them in the right order, you see that that's really kind of one continuous thing going to the right. The integral from 1 to 3 is I don't know what. So that piece is unknown. From 3 to 10, we said was -7. That's that part. But then from 1 to 10, the whole thing is equal to +4. So what must be in the question mark to make the entire thing +4 if you're losing 7 from down here? It's got to be 11. You buy that? Yeah. Okay, so this one is 11. All right, number 10. 10, 10, 10. So using basic properties, before we do number 10, let me just talk about the two other little things here. So first, I gave out answer keys to all the quizzes from the semester last time, but for some reason I have some left over. Is there anybody that didn't get one last time? Okay, one here. The other, anybody else? There you go. Is there a quiz, the answer keys to all the quizzes from the semester? Did you get one?
Yeah.
Okay. All right, so we have news on the physics calculus front. So I think we talked a little bit in this class about how the Calc 2 class was getting very, very full. So what has happened is Calc 2 and Physics 2 have both been split into 2 sections, just like they are this semester. Historically, the 2 sections of Calc 1 merge together and only have 1 section in the spring for Calc 2. Same thing for Physics. But the administration is supporting this split. And I say supporting because it costs more money to have an extra section. So I appreciate that. So it is officially now split, and we have taken anybody whose last name was between A and N and put them into this version of things. So 8 o'clock physics and 1040 calc 2. Anybody who's later in the alphabet is an 840 calc 2 and a 10 o'clock physics 2. Last name. Last name. So here's the deal. At the moment, really anybody can go anywhere. And so if you have a strong preference to be in one over the other, then let me know right at the end of class today or on Monday or something like that. All right, it's up in the air. It's open right now. That said, if everybody decides, oh, I could be really smart and get an extra 40 minutes of sleep by coming into the calculus class first, and there are 33 people in that class, then we haven't accomplished anything by splitting into 2 different groups, right? So we need at least, like 12, 15 people who are willing to do this 8 o'clock physics class. So if you have a very strong preference, like I have to get my kids to the bus stop and I can't be here at 8 o'clock, that's reasonable. If your preference is because you want to hit the snooze button 4 more times, we might have an issue there, okay? So see me after class, figure it out. 10:40 to 11:50, just before noon. Same as physics this semester, I think, right? 10 until 11:50? Yeah. So it'll look exactly like it does this semester. All right, so that is, yes, I'll be doing both calculuses. Ted will be doing both physics. Physics is yeah, physici. Okay. All right, any other questions about that? Sure. Sure, yeah, and there'll be somebody, well, but there will be somebody here 10 to 10:40 in the math studio if you're in the 10 o'clock. Yeah, starts at 10:40. Same exact thing. Yeah. All right. Okay, so we're gonna skip number 11. In fact, we're gonna skip the rest of this stuff. So that's enough. So all right. So we've had a lot of stuff that we've done this semester. Um, None of the things that we talked about, none of the things we introduced today are going to be on the final exam. Just kind of a preview of coming attractions. Calc 1 is oftentimes called the differential calculus, the derivative calculus. Calc 2 is often called the integral calculus. So next semester will be all about integrals, and somehow there's a connection to antiderivatives, which we talked about a little bit last class. So that is that. So here is what we can do for the remainder of today. There was an enormous group activity last time that there's no chance people had a time to finish in class. It started back on page 73. So if you are so inclined, maybe go back to page 73 and pick up where you left off, work with your neighbors and see how far you can get. There are also sample test problems someplace back, so if you decide you want to go back and just start doing some sample test problems, then this is a good time to do that. Again, the videos are all up on YouTube for me going through each of those sample test problems. This stuff right here on 73 is testable on the final exam, all right? So that is fair game. So let's see how far we can get, and I'll walk around and help if I can.